All right, so welcome back to the OneClass channel. So my name is Joey. I'm going to be your chemistry teacher for the next hour or so. We had our session 2 hours ago. And what we did was we answered kind of typical chemistry questions that were asked in kind of between grade 10 all the way up to the organic chemistry university level. So what we're going to do is we're going to continue with that session as well. So I have a bunch of questions ranging from, I believe, I have university, some grade 11, grade 12, and organic chemistry problems as well. So kind of following in terms of that format. If you're tuning in for the first time, thank you so much for tuning in. Thank you so much for watching. What we're doing here at OneClass, if you're new to this channel, is that we are providing kind of online solutions and kind of videos and live streams for frequently asked questions in both mathematics and in chemistry. So that's kind of our motive for and our goal here at OneClass. And me as a OneClass teacher, what I'm doing is I'm verifying solutions for you so that you have kind of the best answers going towards your classes in the future or your classes in the present as well. So just a little bit about myself. My name is Joey. I'm currently a secondary school educator in Ontario, and my teachable subjects are chemistry and as well as mathematics. I'm working towards a mathematics teachable as well. So without further ado, let's get started. I have about 11 questions again for this hour, and let's see how much we get done for the session here. So let's get started. So our first question is asking us a 0.22 caliber handgun fires a 1.9 gram bullet at a velocity of 765 meters per second. Calculate the de Broglie wavelength of a bullet. Is the wave nature of matter significant for bullets? Okay, so this answer is very, very incomplete. I don't know there's no numbers here. There's nothing here. I think the grammar is kind of off. So solution's obviously incorrect or it's incomplete here. So I'm going to write solution's incomplete. But let's solve this problem here. So I have here a 0.22 caliber handgun, right? So let's say this is question one. Let's see, question one here. Let's see if my pen is working. There we go. Question one's asking, so I have a 1.9 gram bullet, and it reaches a velocity of v equals 765 meters per second, and it says calculate, I want the wavelength, the de Broglie wavelength. So this is lambda here, and this is going to be our wavelength of the bullet here. So what do we need to know? Well, we have to figure out what the we know our de Broglie equation here, right? So the de Broglie wave equation basically states that lambda, or the wavelength, equals h, which is Planck's constant, divided by mass times our speed, right? So here is our de Broglie wave equation. It's basically derived from kind of Planck's equation as well, like E equals hc over lambda. And if we rearrange that, de Broglie just found a relationship between the mass and also the energy with those two kind of components, and basically he developed this kind of equation as well. So lambda equals h over mv, and we want to solve for lambda. So this is actually really good. So we want to solve for lambda here, and I have so lambda is already on the left side here. Planck's constant is 6.63 times 10 to the negative 34. So I'm going to say here, and some calculators might have that already inputted, but I'm writing down here 6.63 times 10 to the negative 34. This will be in joules per second here. Is the unit for kind of this equation here. So joules per second, 6.63 times 10 to the negative 34 joules per second. My mass here is actually in kilograms. So what I'm going to have to do is I'm going to have to convert my grams into kilograms, right? So I have 1.9 grams here. I'm going to divide this by 1,000, right? So let me divide this by 1,000. So it's 1 kg. So 1,000 grams in 1 kilogram. I'm going to use my calculator. 1.9 divided by 1,000 equals 1.9 times 10 to the negative 3. So I'm going to write 1.9 times 10 to the negative 3 kilograms here. I'm going to multiply that by the speed, right, which we have given 765 meters per second here. And then this here should equals meters, right? Should equal meters per second here, just because my kilograms times meters per second, or times meters, will give us meters per second squared will give us our joules here, right? So this here would cancel out, and we would basically get our wavelength here. So let me just input this into our calculator here. So So we have 6.63 times 10 to the negative 34 as our numerator. And then we're going to divide it by 1.9 times 10 to the negative 3 kilograms times 765 meters per second. And we're going to get a value of, this is 4.56 times 10 to the negative 34 here. So I'm going to keep I'll keep 2 decimal places, because again, 1.9 states I have 2 significant digits. So this would be 4.6 here. 4.6 times 10 to the negative 34 meters here. And this here is the wavelength of my wavelength of the bullet. So this is the de Broglie wavelength. So here's my solution here. And it's asking us, the second part of the question is asking us, is the wave nature of matter significant for bullets? And in this case, it's not really significant. Like, this doesn't really tell me anything here. It doesn't tell me if I emit some sort of light. It doesn't, in terms of the spectra. If we were talking about electrons here, obviously the speed would be much, much faster, probably about the speed of light, which is 3 times 10 to 8 meters per second here. But again, this speed is very, very slow, right? If we have a very, very slow speed, we're going to get a very, very small wavelength. And this wavelength doesn't really tell us anything about about the bullet here. So in this case, it doesn't, it's because the wavelength here, it says the de Broglie wavelength of the bullet is very small, so it's going to be basically neglected, actually. So its wave nature is not significant for the bullet. Remember, wave-particle duality states that we have particles can exist as a wave here, so in terms of wavelength, and can also exist as a particle, so it also has a mass here, right? So again, the mass here is much more important. Like 1.9 grams bullet, we 1.9 grams, we can measure that, right? If we can measure that, then I guess the opposite is the wavelength here. The wavelength property of the bullet is basically not significant, just because it's so small. So I'm gonna say here solution here is incomplete. Incomplete because no answer was given. And I'm going to say here de Broglie, I'm going to write here de Broglie wavelength equals Planck's constant, so h over m times v. So this is Planck's constant divided by mass of bullet. Maybe put parenthesis around this one. These guys here, mass of bullet times the speed of the bullet, and then basically this would equal, I'm going to keep my formatting here, so this is 6.63 times 10 to the negative 34 divided by, this here is 1.9 times 10 to the negative 3 kilograms multiplied by 765 meters per second, and we get a value of 4.6 times 10 to the negative 34 meters. De Broglie wavelength of the bullet is extremely small, therefore not significant. The wave nature of the bullet is not significant. So I'm gonna say solution here is incorrect just because because no answer was given here. So I'm gonna write solution here is incorrect. All right, that was number 1. We can look at number 2 now. So it's stating, how can I draw the Lewis structure of H2O? So very, very easy question here, number 2. And maybe you can take a moment to think about this problem here. So how can I draw, what is the Lewis structure of H2O? So think about this problem, and then we will you can look at the solution here while we think about this solution here. So I'll give you a moment to think about this problem. Think about valence electrons in terms of oxygen. We have 6 valence electrons. On oxygen, we can think of hydrogens having one electron on the outside, right? So think about those things, and how would bonding affect those things here? So let's draw this out first. So I have H2O, right? Which means I have basically 2 hydrogens. I'm going to say I have 2 let's see, come on, pen. There we go. I have 2 hydrogens and I have 1 oxygen, right? So usually the atom or the element with the most valence electrons belongs in the middle. So I'm going to say O here, and I have 6 valence electrons. So I have 1, 2, so I have 1, 2, 3, 4, 5, and 6, right? So 6 valence electrons, which means that hydrogens have to be on the outside, right? So my hydrogens, I have 1 here, and I can say maybe hydrogens can be 1 here, right? So these are going to bond, right? Like, as you can see here, these 2 are going to bond. It's going to make one bond, and then these guys are going to make a bond. So you can say that I have, so this will become O here. I have 1, 2, 3, 4, 6, 7, 8. I have H here on this side here, and H side on this side. So therefore, you can say that my Lewis structure will look something like this. However, if you want to be technically correct here, again, we have 6 valence electrons on oxygen, 1 electron on hydrogen. These 2 are going to make a bond. These 2 are going to make a single bond as well. So therefore, this is our Lewis structure. If you want to be very, very technical in terms of saying what this is actually, it will actually create a bend structure. So like just because here I have lone pairs on oxygen, right? So here, these guys here, the pairs of electrons that are not participating in bonding are lone pairs. So this here is a lone pair in red, and this here is a lone pair, right? What the lone pair does on this oxygen is going to actually draw electron density, so it creates a dipole moment, right? So I have this oxygen here and oxygen here. These guys, these lone pairs don't like these bonds here, right? So they're going to kind of create a lone pair. So there's actually kind of a partial negative charge on these electrons here. They're pulling electron density away from hydrogen here. So they're partial negative here, and this is partial positive here. So this here is actually a polar molecule because of the dipole moment that exists, and we know it's water, right? So because we have the intermolecular forces, we have hydrogen bonding here, and we also have a dipole moment here. We have dipole. So we have 2 kind of intermolecular forces here. I'm going obviously above and beyond this question here when I say that, but it's saying how can I draw the Lewis structure? This is how you draw the Lewis structure diagram here. So again, this here is our correct answer. And then if you want to form the bonds here, this one is even better here. Use drawing a bent structure here. So this one's technically correct, but geometrically, because of the lone pairs pulling electron density away, it actually looks something like this in terms of Vesper theory when we're talking about lone pairs and creating a bent structure. So solution is correct. Diagram is technically incorrect because of the bent structure, because of Vesper theory that states that lone pairs draw electron density away from the molecule, therefore creating a bent structure. But solution here is correct nonetheless. I don't think you're expected to know Vesper theory anyways in grade 11, so it's totally fine. Number 2, let's look at number 3. So it's asking us which compound CH2F2 or CF4 experience stronger intermolecular forces overall. So I have CH2F2 versus CF4. So let's draw this out. Let's draw the Lewis structure for this one. So we have, so this would probably be asked in a grade 12 question here. Junaid says hi. Sorry, I didn't see your comment, but hello as well. Thanks for tuning in, by the way. CH2F2 here. So again, the atom with the most valence electrons is going to go in the middle, right? So carbon's going to go in the middle, and then I'm going to have basically H here and H here and F here and F here, right? And they all have, we all know that they can, they only need one more valence electron for it to bond. So this means that I'm going to get a bond here, one bond here, one bond here, and one bond here, right? So this here is my diagram for CH2F2, and then CF4 obviously would mean that I have fluorines kind of bonded to this carbon like so. So let's look at the intermolecular forces in this guy here. So carbon here has electronegativity difference between carbon and fluorine, right? So I know that this here makes carbon here partial positive, and fluorine is going to pull electron density away from this carbon molecule here. So this will mean partial negative, and this here is partial negative as well. So I have a dipole that's going from here to here and from here to here, right? So these dipoles, I have a dipole existing in number 3 here, and CF4 here would be, I have electron density being stretched, right? And this is partial negative, partial negative, partial negative, and partial negative. And this guy here is partial positive. So I have basically all these dipole moments going from this way, this way, this way, and this way. All these dipole moments actually cancel out because I have, again, fluorine is on it's on carbon, it's 1 to 4 carbons here, and all these dipole moments actually cancel out here. So these guys all cancel out, which makes this a non-polar molecule here. So this here, the intermolecular force in this is not dipole. In this case, it would be London dispersion, right? London dispersion would be my intermolecular force. And then for CF2, because I have these two dipoles here and I still have hydrogen here, these guys are not fluorine. So this here would be a dipole. I will have a dipole interaction here. So this here would be a polar molecule because I have the electron density is being pulled away from carbon. So in this case, which one would experience the stronger intermolecular force? CH2F2 would experience the stronger intermolecular force. So this solution here is correct. Again, they're saying CH2F2 is a polar molecule. That's correct. Dipole with weaker dispersion forces. CF4 is a tetrahedral structure, right? And this here is a non-polar molecule. You can think of CF4 as CH4 as well. Methane. These are non-polar molecules, and they will have London dispersion forces as their dominant intermolecular force. So the solution is correct. Great analysis here. Okay, number 4 here is asking us, rank these systems in terms of decreasing entropy. Rank from highest to lowest entropy. Okay, so I have this number 4. So we want from highest to lowest entropy. And then that's about it. So how many things do we have here? Oh, this is a long question. I have part B and part C. Wow. Okay, so I might have to actually just go through the solution here, and I might not be able to do it in time. So again, I want to get through 10 questions, but let me just write some of this stuff down. So it says neon gas, half a mole of neon gas, half a mole of liquid neon, and these have different temperature changes here, right? So I have one that's at 273 Kelvin, one at 20 liters, and then one at 100 Kelvin, and I don't know how many liters as well. And then I have kind of other compounds as well. So this is we're talking about terms of an entropy here, right? It's asking, and then part B is asking us classify each process by individual effect on the entropy of the universe. And then you have these guys here. I have to classify them by entropy. And then part C is asking us predict the sign of delta S for each process. And then you get chemical compounds here. So let's see. I'm just going to look at the solution just for the sake of time, and I'll just kind of explain the thought process that they have here. So it says entropy is a measure of disorderedness. The higher disorder, the higher the entropy. So this solution here is correct, right? So this is from going from highest to lowest entropy here. So it's saying here 1 mole. 1 mole here is, so 1 mole, obviously, if you have the larger the compound, the more entropy it can create, right? The more messiness, or the bigger mess it can create, right? So therefore, all the 1 mole solutions would be at the top here, because it's, again, if I have more of a substance here, it can create more disorder, right? So he said, basically I have 1 mole from 1 to 4, and now I'm ranking them by volume first. The higher the volume, as you can see, 40 liters and 40 liters, the higher the volume, again, the more space it has to create entropy. So again, 40 liters will also be correct. And then finally, because it's in constant temperature, we care about basically the chemical structures. We have neon, we have fluorine gas, and CS2, right? So neon, obviously, because it's a noble gas, neon doesn't like to react with anything, right? So if it does react, it's going to create it's going to produce a high measure of disorderness, right? So 1 mole of neon gas at 273 Kelvin at 40 liters is correct. Finally, we have, and then secondly, we have F2, right? F2 is, again, a diatomic molecule for fluorine as well. This is very, very stable as well. So if I want to, again, break this apart, it's going to, again, release a lot of energy here. So again, it'll create a high disorder. And then finally, CS2 here is next, because I have again, it's the last one that has basically a higher volume, and it's going to be basically it's if I draw this guy here, it's basically um, it looks CS2 looks like this, carbon disulfide, and if I break this apart again, it's going to create it has room to create a high order of disorderness, right? So this here makes sense for the first three rankings, and then finally 4, 5, and 6 again, it's lower volumes as you can see, and then also lower concentrations or lower lower moles, so it's a smaller compound. So again, I don't have as much, so I can't create much disorder. And as you can see, we have the neon gas again as first, because neon gas is a noble gas, and we have half a molar of neon gas, which is good. And then finally, a neon gas at a lower temperature at 100 Kelvin and 20 liters, and finally at a liquid form is going to create the least amount of disorder because it's in liquid form. The molecules are more tightly bound together, so they're a lot slower, so therefore it creates less of a mess here. So A here is correct, great ranking. That's good. Number 2 is asking us, I think they skipped part B here. So part B is asking us classify each process. So I don't even know what the classification is here on the entropy, but we can go through this. So it says here, a process run infinitesimally, slowly at equilibrium or reversed to its original state. It says here a constant composition mixture of solid and liquid at standard temperature pressure, STP, motion of frictionless pendulum, a bag of red marbles and a bag of green marbles dumped together on a tabletop, evaporation of water from a cup, isothermal expansion of a real gas here. So I don't know if it's like high entropy or low entropy. I really don't know what the question's asking here for part B. But I'm going to move on to part C here. So it's asking us predict the delta S for each process. And as you can see here, you have water going towards hydrogen gas and oxygen gas here. So again, number of moles here is being increased, right? So hence delta S also increases. You could think of this as this is simply just the hydrolysis of water, right? I'm breaking down one component. It's a decomposition reaction, sorry. And it's going from one thing to more things, which means that my delta S is going to be positive, which is good. And then finally, I have iodine gas going to iodine solid. Physical state is changing from gas to solid. Entropy is decreased due to decrease in disorder. This is correct as well, right? Because I'm thinking of a gas here. It's basically, if you go back to kind of particle theory, gas molecules have a very, very high speed. It takes up more volume. If I bring it to a solid state here, it's going to be very much more compact. So therefore, it's going to decrease in disorder. So I'm going to say solution here is correct. Missing part B of the question is misleading as to what it is asking, but part A and C are both correct here. So I'm going to say the solution is correct because the part B, I really don't know what part B is trying to ask us here. When we say classify each process, I don't know what it's asking here. So I'm going to say, for the sake of time, solution here is correct. Okay. Number 5 is asking, rank the following phenolic compounds in order of acidity. So it's going from least acidic to most acidic. And then we have 3 compounds. So we have a benzene, and then we have this here is HO, and this here would be a C triple bond N. We have this guy here with the HO. And then finally we have this guy as a HO and C triple bond N. Okay, so it's least acidic to most acidic. So if I'm talking about acidity here, the least acidic molecule here has to be phenol, right? Phenol here is the least acidic here, because HO is an electron, it's not an electron withdrawing group, it's an electron donating group, right? So this here, because it makes the conjugate, makes basically the carboxylic anion, it's destabilized by the electron donating group, right? So it's pushing electron density towards the negative charge of the carboxylic. So it basically, in this case here, it's the least acidic, and as you can see, this here says middle molecule is the least acidic. So this here is correct as well. So this here is the least acidic because of the hydroxyl group here is a EDG, right? Or you can say it's electron donating group. So this here is the least acidic. And then as you can see here, these two, I'm left with these two guys here. And these two guys here both have a hydroxyl group, and they have actually an EWG, right? This C double bond N here, the CN group, is a electron withdrawing group, right? So this actually increases acidity. So if I have these two here, and the only difference here is one is in one is in para, or this is an ortho, this is a para position, I believe, and this one is meta directing as well. So as you can, so in this case here, the most acidic atom here would be this left group, right? This left group is most acidic because it's the least stable in terms of its geometry here, or the orientation here, and this here would be in the middle here. So this is acidic as well, because if you look at this this position here, this position here, the kind of directors here, we have hydroxyl group here, and then our CN group here, right? So this is para. So this is a para towards para, because it's creating the maximum amount of distance in terms of the hydroxyl group and the C triple bond N group. So this one is actually pretty stable here. However, for this one, this is meta here, and meta here is creates a higher amount of energy, because this here is not it's not as stable, right? It's not creating the maximum distance between the hydroxyl group and the C and the cyanide group here as well. So this one becomes the most acidic group when being deprotonated here. If this H or if this H is missing here, I can't stabilize it with the C triple bond N here as well as if it was in the para position here. So this solution is correct. It's correct. This is a good analysis as well. They're saying CN is EWG and meta directing, right? So this here is a correct solution as well. So this here is the most acidic here. Would have also talked about meta versus para orientation, and how meta is more acidic than para in this case. So the solution here is correct. Number 6 is asking us, what is the formula for dihydrogen monoxide? So formula for dihydrogen monoxide. So if you look at this compound here, this is a molecular compound, right? Every time I see di and mono here, this has to be a molecular compound. So it's not ionic. So basically I have, it's basically going to contain nonmetals here. So I have hydrogen and oxide here, which means I have basically an H something and an O something here. So hydrogen obviously is in the name, and oxide here is oxygen, so that's okay. So we have HO, and then mono means one, right? So O here means I have one oxygen here. Di means I have two. So therefore I have H2O1, or you can write this as H2O, right? So H2O here is the chemical formula for dihydrogen monoxide. Nobody actually calls it dihydrogen monoxide. We all know that H2O is water here. So this here is the formula for dihydrogen monoxide. H2O is correct here. Solution is correct. Good analysis here of nomenclature of a molecular compound. Nobody calls water dihydrogen monoxide, by the way. This is kind of a trick question here. We just call it water, H2O. All right, number 6. Let's look at number 7. It says, according to Coulombs Law, which pair of charged molecules has the lowest potential energy? So we have Coulombs Law. It says which particle has, I want the lowest PE, or lowest potential energy here. I'm going to write the options here. So it says particle with 1 minus charge separated by by 150 pm from particle with 2 plus. B is 1 minus separated by, so basically the same thing, but particle with 1 plus charge. C here is saying particle particle separated by 1 minus charge by 100 pm from, it's basically from a 3 plus charge here. Okay, so we have 3 options here, and again, this guy again, it's like, I feel like it's the same. Maybe it's the formatting issue, but it's definitely just like a huge chunk here. But it's asking us what is the highest, or we want the highest potential energy, right? Lowest potential energy here. So lowest potential energy. If we look back to Coulombs Law here, it says here, I like the explanation here. It says explanation is Coulombs Law describes the attraction and repulsion of charged particles, right? So Coulombs Law, potential energy between 2 particles is directly proportional to the charge of the particles and inversely proportional to the distance between 2 particles. So I can say, and I can basically write here that potential energy is proportional to the charge, right? So to the charge of particles, and then it's also inversely proportional to our distance, right? To our distance here. So basically, it's saying that as the potential energy increases, the charge also increases, right? So as it increases, as PE increases, charge also increases. And for here is as charge here increases, the distance is going to decrease, right? It's inversely proportional here. So it's asking us we're looking for the option with the lowest potential energy, right? So let's modify this. And let's modify all of these guys to the lowest, right? So if we decrease the potential energy, my charge will also decrease. So it will also decrease here. If I decrease the potential energy here, I'm going to have to increase my distance, right? So if I'm for the lowest potential energy here, I'm looking for charges with PE here has a lower charge here, and I'm looking for PE with the greatest distance, right? So let's look at this. This is the solution here. It says the particle with a 1 minus separated by a 2 plus charge. Substitute the values in equation 1 and calculate the potential energy. So again, there's no calculations here. So let me just figure out what. Let me just write out Coulombs Law for you. Give me a second here. I'm just gonna find out the equation for. Usually, you're given an equations sheet. You're not really expected to memorize this. So I actually haven't memorized the equation for this. But let me just search up the equation for you, so at least I have something to write down for you. Yeah. So if so here it's saying here. Let me write this in blue here. So E, which is basically the potential energy. See if the pen works. There we go. E here is proportional to basically Q1 times Q2, which is the charges of the two particles, times epsilon, or divided by epsilon times R here. Epsilon here is basically the dielectric constant, which is equal to 1 actually. So it doesn't really matter actually. So basically it's just asking us E is proportional to basically, I can say that E equals K, some constant K, times Q1 over Q2 divided by R, right? And R here is simply the distance before them. So what we can do is that we can actually just substitute all of these guys here into this equation to solve for it, right? So in this case, E here equals 1. So I can basically say, and if I want to kind of write an equation, this would be kind of K over Q2 over R, because epsilon here equals 1. In this case, K, I can divide K out as well, right? So I can just say simply E here equals Q1 times Q2 over R, right? So we can use this equation to kind of figure out the potential energies for A, B, and C, right? So A here in this case is 1 minus times 2 plus. So I can say here 1 minus, so I have a 1 minus charge times a 2 plus charge divided by R here is, I believe, 150. So I'm not going to convert them to units because I don't know what, I believe it's meters, but it probably is meters actually, because it's in joules. So in this case, I won't divide out the units for the sake of time here. But we have here 1 times negative 1 times 2 here is negative 2 over 150, and this will equal some value here. And again, I really don't care about the units here. In this case, I'm just looking at potential energies, right? So I'm looking at the absolute value of these guys here. So the next one here, that's for A. So I have negative 1 over 175, 1 over 75. B here says particle with 1 plus and 1 minus. So I'm gonna get basically, if I substitute a 1 plus here, I'm going to get negative 1 over 150. Negative 1 over 150 for B. So this here is A, this here is B, and C here would have been, this is a 1 minus charge, or sorry, 1 minus charge with a 3 plus charge, right? So I have 1 times, negative 1 times 3 here, which is 3, divided by 100, 3 divided by 100, right? So I'm going to have 3 over 100 here. So C here would give me 3 over 100. So looking at these guys here, 1 over 75, 1 over 150, and 3 over 100, you can say that 1 over 150 here is, this here is 6.67 times 10 to the negative 3. 1 over 75 here is 0.01. So again, this here is the biggest potential energy, so I'm going to remove that. And finally, 3 over 100 is simply just 0.03, right? So if I care about the lowest potential energy in this case here, the lowest potential energy would be B, right? B here would have 6.67 times 10 to the negative 3 is indeed our lowest amount of energy, right? And this actually makes sense, right? If I look at B here, particle with 1 plus charge with a 1 minus charge. So again, I have lowest charges here, and the distance is increased, right? It's 150 here, right? So B here would give me the lowest potential energy here. So I'm going to say here solution is incomplete. Solution is incomplete, and I'm going to say here potential energy, according to Coulombs Law, potential energy equals basically Q1 times Q2 over R here. Q1 refers to first charge, Q2 refers to second charge, and R refers to distance between the particles. Potential energy is proportional to charge, like they said before. Therefore, B, option B is the correct answer with the lowest amount of potential energy. And you could say here, because charge numbers are 1 minus and 1 plus, and the distance is the greatest between the two particles. So the solution here is incorrect because I just said, again, the solution here is incomplete. So that was number 7. Let's look at number 8. Number 8 is asking, draw the products of the reaction shown below. Electron flow is indicated with the curved arrows here. So this is an organic chemistry question. So with H3C, bond to the sulfur with the lone pairs. Bonded to 1, 2, 3, and then bond to Cl. And it says here the S is going to, again, come here and be attracted to this positively charged carbon. It's going to kick the chlorine out here. So what is it going to make here in this case? So as you can see here, the sulfur here is partial negative. The chlorine is also partial negative, which means this carbon here is partial positive. So these guys are attracted to each other here. So if this chlorine is getting kicked out here, I'm going to get something like I'll draw out the intermediate here. I'm going to get something like this. H3C, bond S here. So it's bond to 1, 2. And basically, if this chlorine gets kicked out here, I'm going to get a negatively charged guy here. Or sorry, I'm going to get a positively charged guy here. So chlorine's going to leave first, and then finally this negatively charged guy is going to be attracted to this, right? So you're going to get, it's going to basically collapse on itself, and you're going to get something like this. So this is actually an SN2 reaction. I'm just breaking it down into two parts for you so you can see where I get the final product from. So this here is H3C bond S here, and then this will be bonded to 1, and then this here is bonded to another guy here. So I have 1, 2, and then I'm going to have basically 1, 1, and 2. So it kind of looks something like, not something like that. It looks something like this. Yeah, something like, because this sulfur is going to be attracted to this carbon here. So I'm going to get something like so. Something like that here. So let's see if the solution here is correct. I think they drew the wrong solution for this guy here. I only have this question here. This here is not the correct solution. This here is, I think, a solution for another question here. But so I'm not given actually the solution. So this is, I can't actually verify the solution here. So I might have to skip this problem. Again, this I think they wrote another solution for another question here. So yes, one here, and then yeah, because I have 1, 2 carbons here, and then this is going to be attracted to here. So I don't know if it makes something like that, but that looks kind of weird. Like it might make something like that. I don't know. That looks kind of odd. Yeah. But this sulfur is going to basically like bend back to itself. So I don't really know if this here is the correct answer or not. But because this sulfur is then bonded to this guy here, right? So it's going to bond to this carbon here, and then. Or actually, no, I would get something like this. Yeah, I would get something like that. Yeah, that makes more sense actually. Sorry. So this, yeah, so it makes kind of like a little triangle here. So I get something. Sorry. I get something like that. Yeah. Where I have basically the 2 carbons here, and it's bonded to this this sulfur here. So it kind of looks kind of odd here, but that's kind of our sulfur here, and then we have the 2 lone pairs, like so. So this here is our solution here. Again, I can't verify it because it doesn't have, I don't have like a solution here. So I'm going to say solution is incomplete. No solution is given for the question stated above. So I'm going to say it's incorrect just because they didn't state a solution here. That's okay. Let's look at number 9. Asking us, what is the molar mass of sodium phosphate? So what the molar mass of sodium phosphate. So let me get out the periodic table again for you. And when we talk about the molar mass, we care about where it belongs in the periodic table. So let's determine here what is sodium phosphate, right? So sodium here obviously is Na, right? Na here is our sodium. You can look at that through the periodic table. Again, Na is here, right? Na is here, so I know that sodium here is Na. I have the charge of 1+ here, so I'm going to indicate the charge. Maybe I'll do it in blue. Na is positive, and phosphate here. Phosphate you can't really find in a periodic table because it's a polyatomic ion, right? So phosphate is one of these special ones. So you're gonna so you should know that this is PO4 and it has a charge of 3- here. charge of 3 minus here. So given this, we know that sodium, we know our phosphate here. If I were to bond these two guys together, you can use the crisscross method, or you could use the kind of logic where if how many positive sodiums here can I balance out the phosphate anion with, and again I need 3 sodiums here to balance out this 3 minus, right? 3 plus minus 3 would give me 0, right? So again I would have Na3PO4, and this here is the chemical formula for sodium phosphate. And in the formula, how many atoms of each do I have? I have 3 sodium atoms, 3 sodiums here, and then I have 1 phosphorus, and I have 4 oxygens, right? I'm just counting the atoms here. So given that, I'm going to have 3 of the sodiums. So the molar mass of sodium here, I go back to my periodic table, I look at the atomic mass here is 22.99. So I have 3 sodium, so I have 3 times 22.99 grams per mole. I have 1 of phosphorus, and I look at phosphorus here. Phosphorus is a non-metal, exists on my right-hand side here. It's 30.974. 30.974 grams per mole. And finally, I have 4 oxygens, right? 4 times, I know for a fact that this here is 15.999, or you can say it's 16 grams per mole. And you can look at the very periodic table and see that oxygen is 15.999 or 16 grams per mole here. So given that, I simply just have to multiply these guys together. So give me a second. Sorry about that. 22.99 times 3 here, which will give me 68.97. 68.97. I have 1 times 30.974, which is 30.974. And finally, 16 times 4 will give me 64 here. I'm going to add all of these guys up, and I will get my molar mass of sodium phosphate here. I'll get 163.944 grams per mole here. And this here is my solution for the molar mass of sodium phosphate. So as you can see, this is the correct answer, 163.97. I had got 94. Very, very much close enough here. They're the exact same thing, right? 3 times 23.0 gives you 68, 1 times 30.97, and 4 times 16 here. And they all added all those up to find our molar mass of sodium phosphate. So solution here is correct. Good analysis here. And let's see, let's look at number 10. Might be able to do my question 11 for today. Oh, this is kind of upside down here, so I'm going to have to, I'm not going to redraw. This is an IR spectra here. I'm not going to redraw it, but what I can do is, maybe I'll just show you the solution here, just because it's kind of hard for me to like redraw it. But it says, maybe from the IR peak, I have an IR spike at, again, this is an IR question, so in organic chemistry. So it's IR spectra, and I have a peak at, I have a single peak at, so single at 1685. And then that's kind of about it for my guys here, right? That's the only thing it says here. I have some peaks here and some peaks here, but it's not, it's kind of it's a bit more rough, so I can't really determine what these peaks are. So it says which compound matches the IR spectrum above, and these are all the compounds you can get, right? So one here has 2 alkenes and a bromine. B here has it's a benzene group with a hydroxyl, so it's a phenol group here with kind of methyl sticking out. C here is a ketone. D here is a cyclohexane group with kind of 3 ketones that are sticking out of it. E here is a heterocyclic group with a nitrogen and a carbonyl group. And F here is a kind of ketone group bonded with 2 benzenes here. So it says, so the solution says the structure is given with, so they picked this guy here as a solution, right? So they picked the benzene group with a carbonyl linked to another carbonyl and a benzene. And it says the peak in 1685 belongs to a ketone, right? So this here is correct, right? Carbonyl groups have a sharp peak, sharp single peak at about 1700. So this here, basically sharp single at around 1700 cm minus 1, right? So this here is very, very indicative of a carbonyl group. So I can eliminate basically A here, basically, from all of these guys here. So it's basically B, C, D, or E, or F. So this is good. Structure D, E, F has ketone groups. So this here, this here it belongs to a ketone, right? So 1685 is a ketone. So I think 1700 is actually an aldehyde, but both of them are very, very similar in terms of the carbonyl peak. So I'm going to say this here is a sharp peak at 1685 is a ketone, and I think 1700 is an aldehyde. If you can, and again, should be given a list on a test or something like that to figure out the iris spectras, and I believe 1700 is the aldehyde. So this is a ketone group, so which means this one here is an aldehyde, B is an aldehyde, so that's incorrect, and only basically D, E, and F have ketones, right? D, E, F have ketones. And then here, the peak above 3000 centimeters represents a allylic group, right? Or the, this is a double bond C bond H. Therefore, the correct answer here is F, right? So again, you see this kind of little peak at 3000 represents the presence of, I believe this is an alkane group, not a double bond here. So if it's an alkane group, then I have I don't have an alkane for D, E, and F, right? D, E, F it's a heterocyclic group for E, and D here is an alkane group, but it's a cyclic group as well. So basically, the only option here left is F here because it represents the C bond H group. So this solution here is correct. It's a good analysis as well. So again, these peaks here at 3000 here are determined between alkane groups as well, and alkynes, right? So sometimes you look at these groups, and although it's not a sharp peak like 1685 here, these also can tell you the presence of a straight chain alkane or a cyclic hydrocarbon here. In this case, at 3000 here, if there's a small peak here, this determines it basically means that we have a straight chain alkane group like so. So this here is our straight chain alkane group, and this here 1685 is our ketone group here. So solution is correct. Good analysis here. And finally, our question 11, so last question of the day, is asking us, a space probe identifies a new element in a sample collected from an asteroid. Successive ionization energies in attojoules per atom for the new element are given in a table. To what family of the periodic table does this new element probably belong here? And we have some optional answers as well. So we look at this table here. So the first ionization is 0.5, and then it's increasing, right? 0.5, and then it's 1, 4, 5, 6, 7, and 8. So when we look at ionization energy, so again, what is ionization energy? Like a review from my last stream here, ionization energy is the amount of energy that is being put into the element for me to remove an electron. So for example, in this case, this is, let me say this is element X here. So I'm going to name this element X. Element X. So element X here, I'm going to add some sort of ionization energy, and I'm going to get X plus my electron here. I'm going to get rid of my electron by ionizing it. So I'm putting some type of energy, and I'm going to ionize this electron here, or this element here. So my first, as you can see, my first ionization energy is very, very, very small, and then it increases as it goes, right? So if I'm looking at the periodic table here, and then if I know my trends here for ionization energy, so for trends of IE, let me write that down, trends of ionization energy. So as I go from left to right on my periodic table here, as I go from left to right, my valence electrons are increased, right? So if it's increasing, therefore it's going to be much harder for me to basically put energy in to get rid of an electron, right? Because if you think of fluorine, for example, I don't want to get rid of an electron, right? Fluorine it's going to take me a long time for me to get rid of an electron on fluorine here, because I want to actually accept an electron. I don't want to give away an electron. So from left to right here, it's going to increase because it takes me more energy for me to remove an electron. So increases from left to right, and then from up to down here, from up to down here, it's going to decrease as ionization energy is going to decrease. In this case, I only care about the family of the group, right? So in this case, I really don't care about this trend. I care about the left to right trend. And as you can see, this here is increasing 1, 2, 3, 4, 5, 6, and 7. And again, these are the answers you can have here. So which group would it belong? Would it belong to 1, 2, 13, 14, 15, 16, or 17 or 18 here. So if it's going to, again, I have 7 ionization energies here, and the 7 being the most here, it's going to basically increase. This element is probably going to be in the 1 or 2 section here. And just because, again, the first energy, ionization energy, for example, if it was lithium here, it would take me very little to add an electron, obviously. So again, this here would be ionization energy 1, and then 2, 3, 4, 5, 6, and 7. Assuming that 7 is the most here, the group with the highest ionization energy here would be a noble gas, right? The noble gases here are already stable. You don't want to add energy to it to remove an electron, right? So therefore, it's either 1 or 2. And in this case, because I7 here, I'm not given I8 here, or the 8th ionization energy here, this would probably belong into group 2, right? Whereas this here is the first ionization energy, the second, the third, the fourth, the fifth, the sixth, and then the 7th ionization energy landing onto the noble gases here. So as you can see here, 2A is correct, right? It belongs into the second column here. So there's writing here, from the given data, we can see that there's a sudden change from ionization energy from 2 to 3, indicates that 2 valence electrons as removed to remove the third electron. Typically it goes higher as the element consists of 2 valence electrons, so it should belong to 2A here. So 2A here is correct answer, just like I said before. Probably belongs to 2A because the 7th valence ionization energy is the most, and it should be be the most as it refers to the noble gases in group 18 here. So solution here is correct. Great analysis as well. So that's my 11th question for today. So thank you so much for watching the stream. Again, my name is Joey. I stream basically from Monday to Friday. I stream math from Monday, Wednesdays, and Fridays, and chemistry on Tuesdays and Thursdays. So you can kind of tune in and watch me stream and kind of go through these problems as well. Again, you can find all of these pre-recorded videos. They're all uploaded on our YouTube channel at youtube.com/OneClass. So you can subscribe, and click your notifications on and turn those on to basically be posted on every time we post another video. As always, thank you so much for watching. Stay safe, stay healthy, and have a great day. Take care.